Welcome! In this session, we'll explore LeetCode problem number 1201, ugly number 3. This problem challenges us to find the nth positive integer divisible by at least one of three given numbers. Stick around as we break the problem into manageable parts and discuss efficient approaches to solve it. Let's dive in. In this problem, we are tasked with finding the nth ugly number. An ugly number is defined as a positive integer that is divisible by at least one of three given integers, a, b, or c. For example, if n is 3, and the given values 4a, b, and c are 2, 3, and 5 respectively, we need to return the third number in the sequence of positive integers that are divisible by either 2, 3, or 5. Let's take a closer look at how this works through some examples. Looking at the first example, when n equals 3, e equals 2, b equals 3, and c equals 5, the sequence of ugly numbers is 2, 3, 4, 5, 6. These numbers are generated by including integers divisible by at least one of 2, 3, or 5, in ascending order. Here, the third number in this sequence is 4, so that becomes our output. In the second example, for n equals 4, a equals 2, b equals 3, and c equals 4, the sequence is 2, 3, 4, 6, 8. The fourth number, when arranged in ascending order, is 6, which is the result. This systematic inclusion of numbers divisible by the given values underpins the logic of the problem. In example 3, when n equals 5, e equals 2, b equals 11, and c equals 13, the sequence of ugly numbers begins as 2, 4, 6, 8, 10, 11. Notice that numbers like 22 and 26, which are divisible by multiple values, are included later in the sequence. Here, the fifth number is 10, so that's the result for this case. In the final example, where n equals 10000000000, a equals 2, b equals 217983653, and c equals 336916467, the output is 19999999984. This demonstrates the challenge of efficiently handling very large input sizes while ensuring accuracy. To solve this problem, we need to find the nth number in a sequence of integers that are divisible by a, b, or c. A key challenge is accounting for duplicates caused by numbers divisible by multiple values among a, b, and c. This requires filtering such duplicates to maintain the correct order. Given the constraints, which allow for extremely large values, efficient methods are essential. Typically, a combination of binary search and the inclusion-exclusion principle is used to efficiently compute the desired result. These techniques help us handle the large range of numbers while keeping the solution computationally feasible. To start, one of the most intuitive ways to solve this problem is by using a brute force approach. Here, we simply iterate through all positive integers, checking each number to see if it satisfies the conditions for being an ugly number. Specifically, a number qualifies as ugly if it is divisible by at least one of the values a, b, or c. As we find these numbers, we can maintain a counter to track how many ugly numbers we have encountered. Once the counter reaches n, we know we've found the nth ugly number. However, while this approach is simple and straightforward, it is computationally expensive. The time complexity is proportional to O, n asterisk max, a, b, c, since we need to check divisibility for each number up to the nth ugly number. Given the constraints of the problem, this method quickly becomes inefficient for large values of n or large divisors. Additionally, the space complexity is minimal at O(1), as no extra data structures are required beyond some counters and variables for the iteration. The brute force approach, while simple, is not practical for larger inputs due to its inefficiency. To address this, we can instead use an optimized approach that leverages binary search. The key idea here is to avoid iterating through every number sequentially and instead focus on finding the smallest number x such that there are at least n ugly numbers less than or equal to x. This is where binary search becomes powerful. One of the key observations is that the number of ugly numbers less than or equal to a given value x can be calculated using the inclusion-exclusion principle. By combining terms like floor6/f, floor6/b, and floor6/c, and carefully handling overlaps with least common multiples, LCMs, we can compute the count of ugly numbers up to x. Furthermore, the function countUgly, x, which calculates the count of ugly numbers up to x, is monotonic, meaning that as x increases, so does the count. This monotonicity allows us to efficiently narrow down the search space using binary search. By starting with a range of 1 to 10 to the power of 9, we systematically reduce the interval until we find the smallest x that meets the condition count ugly, x equals n. The algorithm for this optimized approach is both efficient and straightforward. First, we initialize our binary search range with low equals 1 and high equals 2 10⁻9, which serves as a reasonable upper bound. Next, we perform the binary search process. At each step, we calculate the midpoint, mid, as low plus, high low, / 2. We then evaluate count ugly, mid, using the inclusion-exclusion formula. If the count is greater than or equal to n, it means that the nth ugly number could be at mid or lower, so we adjust the upper bound with high equals mid. Otherwise, we know the nth ugly number must be larger, so we shift the lower bound with low equals mid plus 1. Once the binary search converges, the value of low will represent the nth ugly number. This approach is highly efficient, with a time complexity of O log, max limit, asterisk log, min, A, B, C, where max limit is 2 10⁻9. The binary search itself runs in O log, max limit, and each count ugly computation involves logarithmic calculations of LCMs. The space complexity remains O1, since no additional structures are required. By leveraging the monotonicity of the problem, this method eliminates the inefficiency of checking each number one by one. Ultimately, the optimized binary search approach was chosen because it strikes the perfect balance between efficiency and correctness. The binary search significantly reduces the number of computations required by narrowing the search space, while the inclusion-exclusion principle ensures that we count the ugly numbers accurately, accounting for overlaps. While the brute force approach is conceptually simpler, it is computationally prohibitive for larger values of n and larger divisors. In contrast, the binary search method scales well with the problem's constraints, making it the optimal choice for finding the nth ugly number. This strategy not only meets the time complexity requirements but also demonstrates the power of combining mathematical insights with algorithmic techniques to solve complex problems efficiently. To solve the problem of finding the nth ugly number, we first need to understand what an ugly number is. An ugly number is any positive integer that is divisible by at least one of the given integers a, b, or c. For example, if a equals 2, b equals 3, and c equals 5, the sequence of ugly numbers is formed by taking the union of their multiples. This means we combine numbers like 2, 4, 6, 8, from a, 3, 6, 9, 12, from b, and 5, 10, 15, 20, from c. The resulting sequence is sorted in ascending order, and our goal is to efficiently find the nth number in this sequence. Instead of generating all these numbers one by one, we use binary search to optimize the process. The key idea here is that we can narrow down the search space by finding the smallest integer x such that there are at least n ugly numbers less than or equal to x. This approach significantly reduces the computational cost compared to brute forcing through all numbers. To determine how many ugly numbers are less than or equal to a given number x, we rely on the inclusion-exclusion principle. This principle allows us to count the multiples of a, b, and c individually, while adjusting for overlaps to ensure accuracy. For example, numbers divisible by both a and b are counted twice if we simply add their multiples, so we subtract those overlaps. Similarly, we add back the intersections of three sets where numbers are divisible by a, b, and c simultaneously. This gives us the formula, count ax equals x // a plus x // b plus x // c x / LCM a b x // LCM b c x // LCM c a plus x // LCM a b c. Here, the least common multiple, or LCM, is used to calculate the overlaps efficiently. With this formula, we can quickly calculate how many ugly numbers exist up to any given value x. Now, using this count function, we can integrate it into a binary search framework to zero in on the nth ugly number. The binary search process begins by setting the initial bounds for the search. The lower bound, low, is 1 since the smallest ugly number is at least 1. The upper bound, high, can be set to n * min, a, b, c, because the nth ugly number cannot exceed this value. At each step, we calculate the midpoint, mid equals low plus high, // 2, and use the count formula to determine how many ugly numbers are less than or equal to mid. If the count is less than n, it means the nth ugly number must be greater than mid, so we adjust the lower bound to low equals mid plus 1. Otherwise, we adjust the upper bound to high equals mid. This process continues until the lower and upper bounds converge, at which point low will contain the nth ugly number. By leveraging binary search in this way, we minimize the number of calculations and avoid explicitly generating the sequence of ugly numbers, making the algorithm highly efficient. The efficiency of this approach lies in the logarithmic nature of binary search. Instead of iterating through all possible numbers, we repeatedly divide the search space in half, which leads to O log max_value iterations. Within each iteration, calculating the count of ugly numbers using the formula is an O(1) operation. Computing the least common multiples, or LCM, involves logarithmic calculations based on the smallest of the numbers a, b, and c. Combining these, the overall time complexity of the algorithm is O log max_value log min_value. The space complexity is O(1), as we only use a few variables for the binary search and count calculations. To illustrate, consider the example where n equals 5, e equals 2, b equals 3, and c equals 5. The ugly numbers in ascending order are 2, 3, 4, 5, 6, and the fifth ugly number is 6. Using binary search, we start with low equals 1 and high equals 10. When mid equals 5, the count is 4, which is too low, so we adjust low equals 6. When low equals high at 6, we terminate and return the result. The binary search ensures we achieve this result efficiently. Here, we begin with two helper functions, GCD for calculating the greatest common divisor and LCM for finding the least common multiple of two numbers. These will be crucial for determining overlaps between multiples of different numbers. Next, we define the main function, nth ugly number, within the solution class. The goal of this function is to find the nth smallest number that is divisible by at least one of the integers a, b, or c. Inside it, we define a nested function called count_ugly_numbers, which calculates how many numbers up to a given limit are divisible by any of a, b, or c. To do this, we first compute the least common multiples of the pairs a and c, b and c, and finally, the LCM of all three. Using these, we apply the inclusion-exclusion principle to count the numbers divisible by any of a, b, or c, while avoiding double-counting overlaps. After that, we set up a binary search with low initialized to 1 and high set to a very large value, 2 billion, to officially narrow down the range where the nth ugly number lies. The binary search works by calculating the midpoint and checking if the count of ugly numbers up to this midpoint is less than n. If it is, we adjust the lower bound to mid plus 1, otherwise, we adjust the upper bound to mid. Finally, once the binary search converges, the value of low will represent the smallest number that satisfies the condition of being the nth ugly number. By returning low, we provide the result of the computation. This approach ensures efficiency since the binary search reduces the search space logarithmically, and the use of LCM calculations combined with the inclusion-exclusion principle avoids unnecessary checks for each individual number. Together, these techniques make the solution both elegant and performant. Here, we begin the Java implementation by defining a helper method to compute the greatest common divisor, or GCD, using the Euclidean algorithm. This method iteratively finds the GCD of two numbers by replacing the larger number with the remainder of their division until the remainder becomes 0. Next, we define another helper method to compute the least common multiple, or LCM, using the relationship between GCD and LCM. The product of two numbers divided by their GCD gives their LCM. Now, in the main method nth ugly number, we set up a binary search to find the nth ugly number. We initialize our search range with left as 1 and right as 2 billion, which is a safe upper bound since we are dealing with large constraints. The binary search iterates by calculating the midpoint and checking if the count of ugly numbers up to that midpoint is less than the desired number n. If it is, we adjust the search range by moving the left pointer up, otherwise, we narrow the range by moving the right pointer down. Once the binary search concludes, the final value of left represents the nth ugly number, which we return as the result. To support this, we define the countUglyNumbers helper method. This method computes how many ugly numbers exist up to a given limit, using the inclusion-exclusion principle. First, we calculate the LCMs for pairs and the triplet of the input values A, B, and C. These LCMs allow us to count numbers that are multiples of A, B, or C, while avoiding double counting overlaps. Specifically, we add the counts for each individual divisor, subtract the counts for their pairwise LCMs, and finally add back the count for the triple LCM to correct for over-subtraction. This formula ensures an accurate count of unique ugly numbers up to the given limit, which is essential for the binary search logic to work correctly. To solve this problem, we start by understanding the goal. We need to find the third smallest number that is divisible by at least one of the numbers 2, 3, or 5. These numbers are referred to as ugly numbers relative to the given values of A, B, and C. To efficiently determine this number, we use a binary search approach. First, we initialize our search range with low set to 1 and high set to 2 billion, which is a large enough upper limit to guarantee we cover the required range. The idea is to narrow down this range until we pinpoint the smallest number x such that the count of ugly numbers less than or equal to x is at least n. In the first iteration, we calculate the midpoint, mid, as the average of low and high. Here, mid equals 1 billion. To determine how many ugly numbers are less than or equal to this midpoint, we use the helper function count_ugly_numbers. For this, we need to compute the least common multiples, LCMs, of the pairs and triplets of A, B, and C. Specifically, the LCM of 2 and 3 is 6, of 2 and 5 is 10, of 3 and 5 is 15, and of all three numbers is 30. These calculations will help us count the overlapping multiples accurately. Now, to count the number of ugly numbers less than or equal to 1 billion, we use the inclusion-exclusion principle. First, we calculate how many numbers are divisible individually by 2, 3, and 5. For 2, this is 500 million, for 3, it's 333 million, and for 5, it's 200 million. Next, we account for overlap by subtracting counts for numbers divisible by the LCMs of pairs. For 6, this is 166 million, for 10, it's 100 million, and for 15, it's 66 million. Finally, we add back the triple overlap for the LCM of all three numbers, which is 30, giving us 33 million. Combining these, the total count of ugly numbers is approximately 733 million. This is far greater than the desired count of 3, so we know the third ugly number must lie in the lower half of our range. Therefore, we update high to mid, narrowing the search space. The binary search process continues in this manner, repeatedly adjusting low and high until the range collapses to a single value. The final result of this process reveals that the third ugly number is 4. Let's consider another example where n is 5, and the divisors are 2, 7, and 13. We initialize our binary search range with low as 1 and high as 2 billion. In the first iteration, the midpoint is calculated as 1 billion. To count how many ugly numbers are less than or equal to this midpoint, we calculate the LCMs. For 2 and 7, it's 14, for 2 and 13, it's 26, for 7 and 13, it's 91, and for all three, it's 182. Using these values, we compute the number of multiples for each divisor. Numbers divisible by 2 contribute 500 million, by 7 contribute 142 million, and by 13 contribute 76 million. Adjusting for overlaps using the LCMs, the total count of ugly numbers is approximately 357 million. Since this count is much greater than 5, we reduce high to mid and continue refining the range. Repeating this process, the binary search eventually converges, and the fifth ugly number is determined to be 8. Finally, in the third example, we are tasked with finding the 10th ugly number for the divisors 3, 11, and 17. Using the same binary search procedure, we initialize the range and repeatedly calculate the midpoint, adjust the range based on the count of ugly numbers, and refine our search. The LCMs are calculated as necessary to handle overlaps, and the inclusion-exclusion principle is used to find the total count of ugly numbers less than or equal to the midpoint. After iterating until the range collapses to a single value, we find that the 10th ugly number is 33. To analyze the time complexity, the solution revolves around two main operations. First, we perform binary search within the range of 1 to 2 billion to locate the nth ugly number. Since binary search reduces the range by half with each iteration, the total number of iterations is proportional to the logarithm of the range size. This gives us a complexity of O log n, where n is the input size. Next, during each binary search iteration, we call the helper function count_ugly_numbers, which calculates how many ugly numbers exist up to a certain limit. This function relies on least common multiple (LCM) computations and basic arithmetic. The LCM is calculated using the greatest common divisor, GCD, which runs in O log min x y time. However, since the inputs a, b, c are constants, these calculations are treated as O1. Additionally, the arithmetic operations to find counts of multiples based on a, b, c and their combinations are all constant time. Therefore, the overall complexity of the helper function is O1. Now, combining these two components, the binary search performs O log n iterations, and since each iteration of binary search calls the helper function, the total time complexity becomes O log n asterisk O1, which simplifies to O log n. Moving on to space complexity, the memory usage is quite minimal. The GCD function, which is used for LCM computations, operates iteratively and requires constant space, or O1. Similarly, the binary search uses a fixed number of variables such as low, high, mid, and temporary LCM values, all of which also require O1 space. Since the algorithm does not rely on data structures like arrays or lists to store intermediate results, the overall space complexity is O1. When comparing approaches, the naive or brute force method would involve generating all ugly numbers up to the nth one by iterating through numbers and checking for divisibility by a, b, c. This would require iterating through up to n numbers, performing multiple divisibility checks, and possibly storing results, leading to a time complexity of O, n, and a space complexity of O, n. In contrast, the optimized binary search approach leverages mathematical insights to achieve a much more efficient O log n time and O1 space. This makes it significantly more scalable for larger inputs. Additionally, when considering best, average, and worst case scenarios, the algorithm always runs in O log n time and O1 space, regardless of the input values for n, a, b, c. This consistent performance is due to the fixed range of the binary search and the constant time helper function. Finally, let's solidify the understanding of why the time complexity is O log n, with a mathematical perspective. Binary search works by having the search range in each iteration, which means the total number of iterations required to converge is proportional to the logarithm of the range size. Since the range spans from 1 to 2 billion, the number of iterations is O log 2 asterisk 10 to the power of 9, which simplifies to O log n. Meanwhile, the helper function count_ugly_numbers performs constant time operations like LCM computations and arithmetic calculations, as these depend only on the fixed inputs a, b, c and not on the input size n. Combining both, the total time complexity remains O log n. The space complexity, on the other hand, remains O1, as the algorithm avoids dynamic data structures and only utilizes a fixed amount of memory for variables and calculations. In this problem, there are several common mistakes that can trip up even experienced programmers. First, not accounting for overlapping multiples is a frequent error. When you count numbers divisible by a, b, or c, simply adding the counts for each divisor without subtracting overlaps leads to incorrect results. This happens because numbers divisible by the least common multiple, or LCM, of any two of these values are being double counted. For instance, if a number is divisible by both a and b, it gets included twice unless you account for the overlap. Another mistake is relying on brute force for large inputs. Iterating through all integers up to a large value, such as 10 to the power of 9, is computationally expensive and simply infeasible due to the massive number of iterations required. Similarly, some solutions fail because of incorrect binary search setup. If the search bounds are not properly defined, or if the midpoint condition isn't verified correctly, the algorithm may enter an infinite loop or produce wrong answers. Lastly, edge cases are often ignored. For example, when a, b, or c are equal, or when the target number is very small, these scenarios can introduce unexpected overlaps or require special handling for quicker termination. Another common pitfall arises from floating-point arithmetic errors. When calculating counts, using floating-point division instead of integer division can create precision issues, especially when dealing with very large numbers. To avoid this, always use integer division to ensure accuracy. Now, from an interview perspective, this problem is as much about recognizing patterns as it is about implementation. Modular arithmetic and the inclusion-exclusion principle play key roles here. You'll want to be prepared to explain how the inclusion-exclusion principle works for counting overlapping sets. Interviewers also expect candidates to focus on optimizing brute force solutions. Specifically, binary search combined with mathematical insights like using the LCM is considered the optimal approach. It's important to clearly articulate the trade-offs, why brute force is impractical, for instance, and how binary search drastically reduces the solution space. Furthermore, demonstrating your ability to handle edge cases early on shows that you're thorough and can anticipate problem constraints, which is a valuable skill in any coding interview. This type of problem has strong connections to other related problems on LeetCode. For instance, consider LeetCode 204, which focuses on counting prime numbers. While the context is different, it also involves an efficient counting strategy. Then, of course, we have LeetCode 1201, the problem we're discussing now, which revolves around the same principles of LCM and binary search. Another closely related problem is LeetCode 878, nth magical number, which similarly requires finding specific numbers divisible by given integers. Lastly, LeetCode 264, ugly number 2, involves generating numbers divisible by specific factors. It uses a priority queue, or min-heap, to achieve this. These related problems often share the same core concepts, so practicing them can deepen your understanding and prepare you for variations in interviews. When considering alternative approaches to solving this problem, the binary search with LCM method stands out as the optimal choice. It minimizes the search space by leveraging binary search while calculating the count of divisible numbers up to the midpoint using the LCM. Although it requires pre-computing LCM values and careful handling of edge cases, its efficiency is unmatched, with a time complexity of O log max_vel *log min a b c. Another approach is brute force, which involves iterating through all numbers and checking divisibility for each. While simple to implement, brute force is extremely slow for large inputs due to its O(n) complexity, making it less practical. Lastly, a priority queue or min-heap approach generates numbers divisible by A, B, or C incrementally. This method can be efficient for small values of n, but it doesn't scale as well as binary search for larger inputs. Each of these strategies has its strengths and trade-offs, and understanding them can help you choose the right one depending on the constraints of the problem. Great work! We reviewed problem number 1201, discussed the key concepts like divisibility and optimization, and highlighted the importance of mathematical techniques in problem solving. Thanks for joining, and don't forget to stay tuned for more coding sessions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!